Okay, Chem team, percent error notes coming at you, and percent error is going to come up quite a bit, especially in your lab setting. Whenever we're doing a quantitative lab, you're almost always going to have to calculate your percent error. And but simply, it's basically telling you how close you are to the correct value. Except you're usually not going to see it written as correct value. It's probably going to be written as either accepted or expected value. So it's how close you are to what you should have actually gotten in your measurements or your calculations. Okay, so let's take a look and see if we can make some sense out of this and start to use it in lab and class. All right, so for our example, to get us started, you go to order your iced coffee in the morning on the way to school because for some reason, you already need your caffeine buzz just to get yourself awake and ready to go. You look at the menu and you see this nice full cup of iced coffee. And this is expected, if you look at it, it's going to be 450 milliliters. So you order your iced coffee, and then when you get it, you actually get this order. And you see that it's not quite all the way up there to the top. They're not giving you what you expected. It's actually 25 milliliters less. So your expected order would have been 450. Your actual order was 425. So if you wanted to actually calculate your percent error, you would use these two values. So the formula you're going to see on your reference table is going to be written like this: percent error equals measured value minus accepted value over your accepted value times 100. Since we're finding a percentage, usually when you are measuring this out or calculating this out, you're going to get an answer that is a decimal fraction. And that's why you're going to end up multiplying by 100 to get you to a nice percentage. Okay, so if we look at our two numbers, we have our expected, this is written as expected and actual. Okay, so the expected is another way of saying you're accepted for the correct value you should have gotten. So this 450 is actually going to go in here for your accepted value. Your 425 would be what you actually measured in the lab setting. So this is the measurement you actually got. So that would actually go in for your measured value. So this is a relatively simple formula, but sometimes it takes a little bit of deciphering to figure out exactly which number's going to go in which spot. Okay? So let's look at it in terms of chemistry settings. A student intended to make a salt solution with a concentration of 10 grams of solute per liter of solution. When the student's solution was analyzed, it was found to be 8.90 grams of solute per liter of solution. What is the percent error of the solution? So we know that we're looking for percent error. That's our goal, is to find that. So if we look at our formula that we have just written down, we know that our percent error is measured minus accepted over accepted. And when we do that, we're going to get a decimal, so you're always going to end up multiplying by 100 at the end to get it into a nice percentage. Okay, so we know that's what we have to find, and this is the formula we're using. So let's look at the numbers that are given to us. Now, we wanted or intended to make this 10 grams of solute per solution. However, the actual value that we got, the measurement that we got, was 8.90 grams per solute. So if we're going to put this into our equation, our 10 grams is going to be your accepted, and our 8.9 grams is going to be your measured. This is what actually was measured in the lab setting. So those are our two values. We're going to plug those into our equation and figure out our percent error. So let's go ahead and do that. Take a look at our values. So our measured is 8.90 minus 10.0 divided by 10.0 times 100. Now, before I go through and plug these in, we still always need to make sure we're worried about our significant figures. So if you look at both of our values here, the 10.0 and the 8.90, both of those have three significant figures in them. So if they both have three significant figures and we are dividing here, that tells us that our answer needs to have three significant figures in it. So when I calculate this out, what I end up getting, if you were to punch it into the calculator, you would end up getting 11%. But since I know I need three sig figs here, I'm going to type it in as 11.0%. So my percent error in terms of this situation in the lab was 11.0%, which means I am 11% off or away from the value I should have gotten in my measurements. In your notes, you have two more examples after this one. So for in class tomorrow, when you arrive, you should have attempted to work out both of those problems to solve for percent error. Good luck. See you in class.